Okay, so let's go through, let's set up how we're going to do this. So we want to ask basically how many, in our sample of, I don't know, 5 individuals, how many singletons do we expect? Well, we're actually going to, that number is just going to be equal to the number of singletons that we expect in this individual plus the number we expect in this individual plus the number in this individual. Because they're singletons, so they're independent, right? A singleton here cannot be a singleton there. So this simplifies things because we can just ask, we'll just focus on one individual and ask how many singletons do we expect that individual to have. Okay, so the way that we can set this up is we can expect, we can look at our different intervals and we can generate the expected number of singletons that our focal individual has in this time. Okay, so let's think about that. So that means that for this first interval, we can do, so we'll call that E1, our expected number of mutations in the first interval for our individual of interest. And that is going to be equal to the relevant mutation, so let's just call that M1, divided by the relevant rate of coalescence. Okay, that's great. So that's for our first interval. So for what about our second interval? Well, there's going to be something that looks similar to this, which is the expected number of mutations that occur on our individual of interest in this time. But we also need one more probability here because we need to account for the fact that maybe our focal individual coalesced at this first time. If it coalesced at this first time, then there are no more singletons because any mutation that occurs there is not going to be a singleton, it's just going to be, because this mutation would differentiate these 2, not 1, individuals from these 3. Okay, so we need our relevant M2 and our relevant C2 times the probability not yet coalesced NYC and the probability that after one interval it's not yet coalesced. Okay, so then we've got something similar for the third interval. And actually we've got a funny one that we'll get to in a moment. And so that'll be our mutation of funny divided by our coalescent rate of funny times our probability of funny that's not yet coalesced. So we'll get to this when we get to it. So let's just take this one at a time. Okay, so what is M1 and MC in this case? Well, our M1, remember, we're just following one sequence, and we want to ask, so our relevant mutation rate is the mutation rate in that sequence. So it's no longer U times 5, or U times N, it's now just U. Okay? And then, so what's the rate of coalescence? What's our C1? Well, remember here, right, so, not remember here. Our C1 is just our normal C1, which is just we're waiting, because we're just following, we're waiting until this first coalescent event, whoever is involved in the coalescent event. And so we said that was n choose 2 over n. Okay, so this is the expected number of singletons that arise in our sequence of interest in our first interval. Okay, so now let's go to our second interval. So for our second interval, the mutation rate, so we're going to, this is going to be, given that this thing hasn't coalesced, how many mutations occur? And then this is going to be, what's the probability it hasn't coalesced? Okay, so here, this is still fairly straightforward. This is U divided by n minus 1. Because now we only have n minus 1 lineages, because one of them has coalesced. So that's easy enough, and actually why don't we just go ahead and follow that down through here. So those are our left expressions. And now let's figure out our right expressions. Okay, so after the first coalescent, or rather, sorry, before the first coalescent event, how many lineages do we have that are not coalesced? So what's the probability that this one is not yet coalesced? Well, of these 5 lineages, 2 of them participate in the first coalescent event. It could be these 2, these 2, these 2, these 2, but it's 2 at random. So the fraction that do not coalesce is equal to 3 out of 5. So 3 out of 5 lineages do not coalesce. So the probability that this one does not coalesce in our first interval is equal to 3 over 5. Okay. So then what's the probability that this individual has not coalesced by the second coalescent interval? Well, that's going to be equal to the chance it did not coalesce in the first interval. So that's the chance that it's still going here, times the chance it does not participate here. Well, let's draw that out. So assuming our individual does not coalesce here, so what's the chance it does not coalesce here? Well, now it's going to be 2 out of the 4 lineages that remain that are going to participate in the coalescent, in this next coalescent. And so the probability that our sequence is still not coalesced is going to be equal to 2 divided by 4. Okay, what's the chance that it does not participate in the next coalescent event? Well, here we have 3 lineages, of which 2 out of 3 coalesce. So the chance that it's not yet coalesced is 3/5 times 2/4 times 1/3. Okay, so actually, and we can, so let's systematize this. And so let's recognize that 3 is n minus 2, and 5 is n. So then here we have n minus 2 over n times n minus 3 over n minus 1. And then here we have n minus 2 over n minus 3 over n minus 1, and n minus 4 over n minus 2. Okay, so then we can also recognize here that in our that this n minus 1 n minus 1 choose 2 can be written as n minus 1 times n minus 2 over 2. This is n minus 2 n minus 3 over 2. This is n minus 3 n minus 4 over 2. And actually, here we can rewrite this as u equals n times n minus 1 over 2 over n. Okay, so we can do some simplifying here. So we can get rid of these n minus 2's. Here we can get rid of the n minus 2's and the n minus 3's. And here we can get rid of the n minus 3's and n minus 4's. And so then this becomes u over n minus 1. And I'm going to move this 2 and this n up to the top. So 2nu. Here we also get 2nu divided by n times n minus 1. Here we get 2nu divided by n times n minus 1. And what you see is that in general, for each one of these, you can see that even though it was a little bit of a bear to get there, here these correct out. And again, we get 2nu divided by n minus 1. So from all this, leaving aside this last one, from all this, basically we get 2nu divided by, let's take this one step further. We can recognize that 2 divided by n times n minus 1 is just 1 over n choose 2. That is, this can be rewritten as that. So each one of these is equal to this. And so we can so our total value then, summing up all these things, is equal to 1, 2, 3, 4, or n minus 1, the number of n intervals, times nu over n choose 2. So I think this is really remarkable that we can write down something this simple that is the result of this complex process. And actually we can recognize that we can simplify this further, because this is equal to n times n minus 1 over 2. And so then we can correct out these n minus 1s. Sorry, let me take this, let's wait one step for that. Okay, so but we see that there's actually an opportunity to simplify this yet further. Okay, so we've left out this funny part. So this funny part is this branch right here. Okay, so we've said the number of singletons is equal to the number of mutations that occur on this branch, plus the number that occur on this branch, assuming this hasn't coalesced yet, plus the number on this branch, assuming it hasn't coalesced yet, plus this. But if, in fact, it hasn't coalesced all the way to the end, I want you to recognize that mutations that occur here also make singletons, right? So in this case, it would be if there's an ancestral C, and that C would mutate to an ancestral T, and that T mutates to a C. Well, now all 4 of these individuals have the new allele, and this one has the ancestral allele. But from the perspective of how many singletons there are there, what is the frequency of the rare mutation, this is still just as much a singleton as the ones we've been studying. So this is the funny one that we need to take into account. Well, we can recognize actually that if coalescence has not occurred here, that basically this branch is the length, that this branch is the number of mutations we expect to occur here, if coalescence has not been reached yet here. So this is the number of mutations that occur in a single lineage in the 4th branch, or M4, divided by the coalescent time, C4, times the probability that it is not yet coalesced here, which is actually just P sub 3 of NYC. So actually, this branch, the contribution of this term to the singletons is actually the exact same contribution as this one, right? These are 2 branches of the same length with the same mutation rate, both dependent on coalescence not having been reached here. And so actually this is just one more of these terms. One more 2nu, one more 2nu over n minus 1, which is equal to nu over n choose 2. Okay, so now we can sum up all of these. And so now we have 1, 2, 3, 4, 5. We have n of them. So we have n times nu divided by n times n minus 1 divided by 2. And we see that we get these n's cancel, and our expected number of singletons is equal to this. Okay, so we just have one more step here. This is the number of mutations of singletons that we expect in this individual, but we have an equal number for each one of these other individuals. Every argument we've gone through for this one equally well applies to these others. So actually, this ends up getting, we can just multiply that by n for our number of individuals, our number of alleles, and we get our total expected number of singletons. So our expectation of the number of singletons is equal to 2nu times n divided by n minus 1. So I'll just make one more point, which is that if n is large, if we have a sample of 20 or 30, then actually n divided by n minus 1 is very close to 1. And when n is large, this just goes to 2nu.